All right, hey everyone, my name is Kendall. I work on a company called Proximity that does a lot of research and development for the Near ecosystem. Just last week, we had a very exciting release we are calling Shade Agents. So the TLDR right there on the screen, these are truly autonomous, and we really do mean that, non-custodial, multi-chain agents. So agents are very hot right now, mainly outside of crypto, but even inside of crypto. These are just a few of the many projects that are launching different types of agents. On the Web2 side of things are moving very quickly. Probably some of the most exciting things you've seen is like the operator from OpenAI that can actually control your screen. We have Anthropic that has a similar type of product. Like they've developed an entire standard for how agents can interoperate together. But for the most part, they don't complete many actions for you because they really do struggle with authentication, payments in particular, and really anything that involves confidential information. So that's the Web 2 side of things. On the Web 3 side of things, most of these projects here are super exciting, but I would classify them as like frameworks in the case of Arc, ELIZA, et cetera. We have Virtuals up there. They're also a very cool project, but similar kind of a framework and then a launchpad. And then we have things like AIXBT, which has done an amazing job of generating a ton of traction. It's like probably dominating mindshare more than just about any other entity on crypto Twitter. But it's mainly a Yap bot is how I describe it. I think Freysa in particular, that's the one with the green hair, is probably one of the more interesting experiments. They were also kind of just the interacting with the agent, trying to talk to it, but you could actually try to extract money from it, which is kind of like a fun way to turn prompt injection into a game. So basically the TLDR and the way agents are today, they can get information really well. They can kind of get you to the point of taking an action, but generally they're not very good at actually taking that action. And there's a few reasons why. So I mean, I think this is there's a couple of things that you need in order to have a truly autonomous agent. I think the most important end result is that they can actually complete any workflow for you end to end, which includes payments, includes actually going out into the world or the internet or wherever it is and doing something. But yeah, we're going to focus this mainly on how we can build autonomous agents in the Web3 space. And so these are some of the criteria of how you actually create an autonomous agent, like what you sort of need. The first one is probably something people don't think a lot about, but we actually think it's one of the most critical pieces, which is this idea of decentralized key management. What we mean by this is that agents are going to need some set of keys that they can interact with, but those keys actually need to be able to be interacted with by multiple instances of the agent. And the reason for this is that if you have a key that's too closely embedded into like where an agent is actually running, what that means is that if that agent fails for any reason, that key is lost, and thus any funds or any authentication that was dependent on that key is also lost. In crypto in particular, this is kind of the most fundamental piece, right? Is that like basically not your keys, not your crypto. So if you don't actually have persistent access to the key and authenticated access to the key, then everything that was a result of that key, which is literally everything you were doing in crypto, is lost. So we actually think that first piece is incredibly critical. Unfortunately, that's something we've been building in Near for quite some time now with a product we call Chain Signatures. Getting into some of these other ideas here. So we also think it's very important that you know exactly what your agent is supposed to be doing. And one of the easiest ways to do this, if you can, is you verify the code that's running. And ideally, you even verify the models that are going to be used to kind of perform some sort of action. So what we've been doing is working on ways that we can actually provide these guarantees as much as possible. And then getting into some other very important aspects, but kind of, I guess, further afield is like you do want uptime guarantees. The Near AI team launched a really interesting paper called Proof of Response that's basically designed to solve this problem. We've been investing very heavily in this idea of trusted execution environments that are very good at verification, but they don't actually guarantee you uptime for any reason, and that's what Proof of Response is designed to resolve. And then some other things that I think are going to become best practices but are still a bit nascent and new is this idea of using smart contracts more as like guardrails for these models and these agents rather than as like where you actually code the agent itself. I think realistically, given that agents require a lot of off-chain compute, they require a lot of access to off-chain data and state, you actually want to use smart contracts more to keep them on track and make sure like, hey, this agent is proposing to take this action. It's proposing to deposit my money into Aave. Well, I want to know that, that like Aave is a good, not a good app. It's like somewhere that I want my money to be sent to. Like that basically we think smart contracts can be used very creatively to actually keep these agents doing the things they're supposed to be doing. And then last but not least, most of these agents, when they're acting on behalf of a single user, they should be kept as private as possible. At least the actions that they're taking. I mean, the second you touch a blockchain, that's mitigated a bit, but like the decision process that goes into making that, that action, your personal data that might be a part of that decision-making process, all that should be kept private. And so what we did is like sought out to create a system that can give you those assurances. So yeah, basically what we call them is shade agents. We are convinced that these are currently the first truly autonomous agents because they actually hit each of those points. And we'll go through exactly how it works. So here you can see a diagram of basically the shade agent stack. There's actually two components that matter the most here. So the first, and you see this is like in that kind of trusted execution environment banner, is this worker agent. This is basically what you think of as like an agent. This is what most people are building when they're building an agent. Usually it accesses some, or like there's some wake up condition, okay, agent's gonna run, whatever that is, like someone requested, agent, go do this for me. Then there's some access to some data, some state, maybe that's information about the user, maybe that's information about like the price of a current cryptocurrency because it's gonna decide to make a trade or not. And then finally there's like some LLM or model, doesn't have to be an LLM, could be any sort of model where there's gonna be basically like a decision-making process that'll be resolved. And then finally, once that decision is sort of finalized and the agent's like, okay, I want to go, I want to take this action, then that action needs to be sent for execution somewhere. So that's the worker agent. That's running inside of this trusted execution environment, meaning that the actions that are taking inside of this environment are only known within the environment. There's no way to exfiltrate or no easy way to exfiltrate the data from here. And also it means that this code cannot be changed without basically wiping the whole environment and thus, we'll talk about in a second why, like basically removing any of the information that's in there. The second major component is the smart contract. So we're using the smart contract for basically three main things, as you can see there. The first is to actually register this worker agent. And what we mean by register is that this smart contract is going to require that this worker agent actually submits basically a proof of the code that it's running. This does this using kind of a primitive of a trusted execution environment, which is called an attestation quote. So basically what will happen is that the environment itself, in this case, like let's say an Intel CPU running this special environment, will actually generate a quote that shows the exact current state of this environment. So in our case, the most important thing it's going to be showing is the code hash of what's actually running in there. And then all of that is basically, it's signed by a key that's embedded within the hardware itself. And then that key is basically attested to by Intel in this case, who's saying, yes, that's actually one of our CPUs that we sold. We verified that like it should be, you know, the integrity should be intact. And so the smart contract will actually take that quote, it'll confirm the signatures from Intel are valid, it'll confirm the signature from the hardware itself is valid, and then it'll actually extract that code hash and check that it matches the code hash that the developers of the smart contract, the deployer of the smart contract, set as like this is valid worker code. And what this means is that anyone can actually spin up this worker agent on their own, you know, assuming they have the right device, their own device, submit this quote to the smart contract, and then all of a sudden they're now a registered instance of a worker agent. This is important because what this means is that if any of these worker agents go offline, anybody else can spin up a new one, which gives you the resilience that's important for like actual autonomy. And then finally, what this smart contract is going to do, at least in what we think is the best practice, is if you take advantage of the feature we have, which is chain signatures, which TLDR is that a smart contract can sign transactions. Basically, we've given smart contracts keys via a decentralized multi-party computation network. Then what the worker agent will do is actually request to send a transaction on behalf of this whole system. The smart contract will verify that the worker agent is registered, verify that the transaction they're requesting is one that makes sense, that fits some rules, and then they'll actually go out, sign the transaction using the smart contract's own key, and then finally send that to the network. And we'll actually walk through the code that shows how that works in a second. So yeah, here's kind of another flow of how the process works. So it's like step one, deploy the smart contract. Step two, anyone can deploy a worker agent. And there's a couple of like helper steps that we've created. You have to, each worker agent will have a near account because ultimately it's sending near requests to the smart contract on near in order to like send these transactions to the destination chain. So there's like a funding step. Then you also check like, is this worker agent registered? Because if it's not, you can call the smart contract, but you'll get rejected every time. So you have to complete that registration step. And then finally, you can actually then make requests to the smart contract to send transactions, and it'll approve these signatures, and then actually complete these actions for you. So how this is different from current T implementations. So it's become in vogue, I guess, to run crypto agents in a trusted execution environment because those are seen as at least better security than running it on just like some random hardware somewhere. The problem is that for the most part, these Ts they have a key that's embedded in them, and that's good for security because that means that someone else doesn't have that private key, and they're not misrepresenting that only the T can basically perform actions using this key. The problem though is that if anyone is able to pull the plug on this physical hardware, that key is lost forever. And that's important. That's a really important security feature, but it does mean that you can't actually trust that any of the funds you send to this key are always going to be there, which is like an insanely, it makes zero sense. Like that's not, we don't think that's like viable at all. I would not recommend you send your funds to any of these kind of agents. And so what we set out to fix with the Shade agent is that the worker agents are basically jointly able to use the same set of keys. So the keys are persistent, they'll always exist, but the only way you can actually request these keys to sign and do something is if you register and you prove that you're running the right code in the T. That's kind of the TLDR of this whole system. So here, yeah, we kind of show like how you can basically deploy one of these worker agents. It's actually pretty simple. If you use a product called Follow Cloud, they provide a really, really nice way to deploy these agents. So you can basically build your application, your worker agent using Docker. That'll generate a unique hash that is basically like the hash of the code that you're actually running. And then all you have to do is basically create this Docker compose.yaml and deploy that using Follow Cloud, and your worker agent will be up and running. And then here you can see actually the code of, this is running in kind of our example worker agent. So what's happening here is we're generating a key within that trusted execution environment that will only ever exist in this instance. And the point of that is that if this worker agent goes offline, that key is lost, which is an important part of like the security properties of this thing. But you can then just spin up a new instance. You'll generate a new key, that's fine. You just have to re-register. That's all that means. And then here you can see we're actually getting the code hash of this, creating this attestation code, and then calling that register worker function on the smart contract, basically proving that within this instance of this worker agent, we're actually running the correct code. And yeah, here, so we built like basically a reference smart contract that actually implements some of these methods. So we've got two basically helper methods. One is this owner, just basically checking like, who's the owner of this smart contract? Who can update this code hash? In a best practice, this should either be immutable. You should just not actually have an owner, meaning the code hash can't be changed. Or, if you want your system to be able to be developed over time, this should be either like a DAO, or I guess like, worst case, like something like a multi-sig. And then we also have this kind of, you see there that like method A, that's basically requiring that the caller of that method, which will ultimately result in a transaction, is running with a given code hash. And so one way you can actually use this is you can have different agents that perform different functions. They'll each have different code hashes, but then you can have like basically, maybe there's like 3 different types of agents you want to run in one system. They each have different code hashes, and you'll have different methods that will pertain to those different workers. So one worker might be able to like rebalance funds across lending protocols. One worker might be able to make trades. One worker might be able to update the whole system. And they can each basically be authorized to call different functions on the smart contract. Yeah, here's kind of just another way to sort of view that. Cool, so we're gonna go through all of that in more detail in just a minute here, but let's zoom out a little bit and talk about like what can you build, like why is this interesting? So 4 major areas that we've identified, and I mean frankly this is probably just the beginning. I think actually one of the most interesting use cases for agents is taking a look at the DeFi apps that exist today, recognizing that just about all of them have a critical component of humans in the loop, and thinking about like where can you actually remove some of those humans in the loop, or what new types of applications could you build if you could have some sort of intelligent decision making that could happen very rapidly, which is like one of the clearest advantages of something like AI versus having to like have this kind of slow, necessarily slower process of having humans in the loop. So it's like that's one really interesting way to think about like, imagine you could just replace a DAO with some agents, and what would that enable you to build? I think another way to think about what you can do here is that because of the fact that we're running a lot of the core logic of this system in something like a trusted execution environment that can itself have sort of verified access to the internet, meaning it can call off-chain data providers, and I mean at least know that that it's going to consistently call that route. You still have to trust that that like URL is going to serve the right data, but basically this enables you to more flexibly utilize off-chain data without having to like get an oracle spun up for specifically that purpose. And think about and then think about if you can act on this off-chain data, but then also utilize any type of model in order to make decisions. So we have a couple of example ideas there. We think like, a very basic one is just a lending optimizer, right? Where you can delegate effectively your funds to this agent. It'll then look for the best rates on a set of lending markets, and it'll rebalance your money across these over time as it notices that things are changing there. And then last but not least, I think like you can actually create interesting markets for basically anything that's digital. We've seen some experiments already where people are like letting you pay for a single use of an API key. So I mean, a basic one could be OpenAI itself, right? Like you want to send a request, like a prompt to OpenAI's API and then get back some sort of response. You can actually create a protocol where you can basically delegate, anyone could delegate a single call and then have you pay them for that single call. Which could get really interesting. Another area that we find pretty fun, and I'll actually zoom out and show you exactly how this works today, is this idea of a headless UI. So because these agents can be tracking interactions basically anywhere and then respond in a verified way, you can actually remove the idea of creating a new UI and like let people, for instance, interact with your application entirely through something like Twitter. So let's actually show how this can work because we built an example. All right, so we built this agent called Shade Agent 007. Basically what it does is it listens to any sort of request for its name. It then analyzes the body of the tweet and determines, is this throwing shade? Is this like a negative tweet? Is this saying something positive? And then it determines which token it's going to send to the user. And so right now we have the user including their account in there, but you can actually even get rid of that. So I'm going to send this tweet. I'm actually not sure whether it's going to frame this as based or shade, but let's find out. And it takes about a minute to respond. But yeah, so basically the idea here is that you can have any sort of existing interface where users are able to interact either directly with these agents or even just make any sort of comment. These agents can then see, okay, cool, there was a request that was basically effectively came to me. They're like, this user is trying to do something, and then it can perform an action on their behalf. So you could even have like an entire wallet that's built into x.com where users could say like send X tokens to this address, and then the agent would be able to respond and actually like, take that action and actually do something. Let's see if it's, and then last but not least is this idea of web markets. And so for this one, we actually worked with the UMA team to come up with a initially very basic demo, but one that I think is pretty interesting that can basically create user-generated markets. And these markets can be agent-settled, they could be agent-resolved, they could be agent-traded, and they can access any sort of public API or private web data. So we think this opens up like a lot of opportunities to basically trade based on digital information and digital information. All right, let's check back in on our bot and see if we've gotten a response yet. There we go. Cool. So it actually sent me these base tokens, and this is going to be on Hyperliquid. So let me, yeah, we'll come back to that one during the workshop. But basically, I'll show you guys that I actually received those tokens on the Hyperliquid mainnet. So basically what it did is this agent looked at this tweet, determined that this was a positive tweet. I guess it's harping more on the age of AI execution than on my comment about AI slop. And then it basically decided to send me these tokens to this address on Hyperliquid, which is pretty cool. So I welcome anybody to try it out. If you tweet at shadeagent007, include your address there and then say whatever you kind of want, and it should respond to you and actually send you some real tokens. They're technically soul-bound tokens. They cannot be transferred, but it's still pretty fun. You will be able to see them in your MetaMask wallet. All right, so now we can actually just go ahead and hop into a specific example. So we will be walking through this template. And if you want to follow along, I recommend you go to nearai.ai/shade, and then you can actually just scroll down just a little bit, and you can see the template itself. And then we'll go ahead and walk through this code. But first, I'm going to show you guys what we built that uses the UMA optimistic oracle. So what's cool here is like you can actually see this URL, like this entire UI is being served from within this trusted execution environment. Generally, that's a bad idea because like you basically want to minimize any sort of access to this environment that you can. Ideally, you have this environment only calling into the smart contract, and that's one way rather than two-way. Otherwise, you do open up some attack vectors. But for the purposes of this, we figured we'd make it a bit simpler and actually have a UI that's still being served from here. So what we're going to do here is we're actually going to take some of the resolution criteria from a recently settled market on Polymarket. So we'll take this one. This is from, what is this here? It's the most passing yards on Championship Sunday. So this was resolved about a month ago, but never too late to kind of check out what's happening. So we'll go ahead and post this in here, and then I'm going to click Submit. And then so we can see what's happening, I'm going to pull up the logs here. All right, let me check this environment. Let's do this. Cool. So you can see here, it's like checking a couple things like my balance, checking the key, making sure that I'm actually authenticated to call this method. Then here you can see it's actually, this is the input of, okay, this is the market that we're aiming to resolve. And then you can see here, it's basically has now like authorized that I can call this transaction, that I'm able to actually send this signature. It's generated the signature here. This is going to be the address on Ethereum Sepolia that it's sending to. And then bam, it looks like we're sent. So where we can actually check this is on the UMA testnet page itself to see like, did this actually send? And let's see. It looks like this is ours right here. Yeah, this is our market will resolve according to whoever had the most passing yards. So we've actually now basically from here, yeah, we think we have a success. So from here, we basically said, okay, this is the market that we're looking to resolve. We entered that in. What happened then is that, and we'll actually walk through this here. Let's walk through what happened. So this question came in here. Well, this is like us kind of making sure that we know which address to call. So basically this question came in. This is this question string. Then we passed it to Perplexity. Basically asked Perplexity like who had the most passing yards on Championship Sunday. Perplexity then searched the internet, used its LLMs, basically took probably, I guess, their like Google data plus their LLM and determined who had the most passing yards. And then we actually went and we like this is all in the worker agent. We generated this request to actually send to the contract saying like, hey, we've determined we want to take this action. We're going to prove we're a verified agent where we have the right to basically call this smart contract. So here you can see us actually constructing the transaction. And yeah, so we're going to call this assert truth with defaults on the actual UMA contract. We're going to do this on Sepolia. And then here we actually put the transaction together. So we've got the address, the chain ID, the actual like transaction call itself. We generate this unsigned transaction request, and then this is where we actually call the near contract, is with this like complete Ethereum transaction. So what we're actually going to do is we're going to send this transaction request, this unsigned transaction, to the near smart contract. And we can actually look at the near smart contract here. So we have this get signature function that's going to be being called with this this payload, which is that unsigned transaction. And then it's actually going to like basically call the chain signatures contract, which will then give us the signature back. And then once we have that signature back, we can reconstruct the transaction, like complete the transaction, and then send it to the Sepolia network. So we basically completed this loop of like worker agent that's going to be responding to these requests. That's running in this trusted execution environment. It registers with the near smart contract, says I'm running this code hash, this is verified code. This is only running with this in this trusted execution environment. The near smart contract whitelist that agent so that that agent can then send arbitrary transaction requests. And then what we just did is we sent that arbitrary transaction request of actually calling out to the UMA contract. So that's basically the flow of what actually happens. So now let's dive a little bit deeper into the structure of this repo so that you guys can kind of do this yourself. So as we said before, there's those two main components. There's that worker agent and that smart contract. We'll look at the smart contract first because it's a bit simpler. So basically in this contract, we've got just a couple of files here. So primarily we've got this lib file. So you can see here we have an owner ID. We'll have these approved code hashes, and this is what initially the owner ID can basically add to. And again, in best practice, this is either immutable or managed by something like a DAO. And then we'll have these worker agents, these registered worker agents. They can be registered by ID, and they'll also have a mapping to a code hash. And then you see here, we'll just initialize it. And then the most important functions, even more so than the require owner, is this require worker. So this require worker function, basically what this is going to do is this is going to tag a specific function as can only be called by a registered worker agent. And so what it's going to do is check the account ID of anyone who calls this, and then determine are they basically in the approved list, and then look at their code hash and say, okay, this worker agent is running this code hash. Does this match one of the whitelisted code hashes? And then here you can actually see the registration step itself. So this is what the worker agent will call when it's first getting set up. And you can see here we're actually picking apart the collateral they sent. This is basically that attestation quote from the trusted execution environment. And then we're going to actually call out to this collateral contract and run this verified check, which is basically looking at all of its signatures and making sure that they're valid from both the hardware, the hardware itself, and from, in this case, Intel, since we're using Intel TDX. So that's the contract. So basically, for the most part, you guys can fork this contract, use it as is. The only thing you have to do is add additional methods here. Like I showed before on this UMA bot, is we had that kind of basically the one to get the ECDSA signature. That's all you have to add, and then you're pretty much off and running. And then we can look at basically this worker agent, which is effectively the rest of the code base. So we set it up as a Next.js app to make it really easy to handle this registration step, because it is a bit involved. You have to generate this quote, you have to generate a key, and then you have to actually call the near contract, and you have to fund your account first. It's possible to do all of this through the CLI, but we just wanted to make it simple, so we put together this Next.js app. So you don't actually have to change too much. I would say you can mostly keep that part out of the box. What I'd recommend changing is if we go to the pages here, you're going to want to add routes to this API folder. Because basically right now it's just set up, this is just basically the registration logic, so it's not actually doing anything. But if you add, say another call here that actually does something interesting, and you add basically a file to this, this API folder, then you can actually perform an action. And so if we go look at my UMA example here, then I can show you the action that I added. So we'll go ahead and open up my code here. So you see here, I added this UMA file here. I also added to this index, I added this handle question submit. That's basically that form field that I was using. And you can see that what happens when someone enters some data into that form field is I call this UMA API route. And so here is where we're actually doing the kind of interesting stuff. So this main function here, this is what's called when you call that UMA route. So the first thing we're going to do, we're going to generate that the address. And so what we're doing here is we're actually determining what address we want to call from on the EVM side. And so this is basically the way chain signatures works is each smart contract basically has a deterministic address. It can request transactions to be signed for. And so the inputs to that, there's basically a master public key of the MPC network itself. We have that in the docs. It's super simple to get. There'll be the actual account ID that you're calling from. So this is basically your account ID of your near smart contract. A path, which is just an arbitrary string. The reason for this path is that you can basically control n number of addresses on a destination chain. And then finally, like the chain itself, like what type of chain. In this case, it's an EVM chain, so we're going to include that here. But you can also do this for Bitcoin. Very soon, you'll be able to do this for Solana and basically every other chain. And then, yeah, we basically take the question string that was being asked and do what we were talking about before, calling Perplexity, getting the result from Perplexity, constructing a transaction, and then actually sending that transaction first to be signed, like verified and signed from the nearest smart contract, and then finally to actually be relayed to Ethereum. And so the important thing to remember here is that you can actually do this for basically any chain. Right now, any ECDSA chain, any chain that supports ECDSA signatures, within the next few weeks, you'll be able to do this for any chain that supports EDDSA signatures, which at that point means you can pretty much call any chain. So yeah, that's pretty much the structure of this project. So yeah, we'll probably have a little bit of time for questions, but I just want to make sure you guys have this link. So again, just this is the link to go to basically get the docs of how to build a Shade agent and then get redirected to that repository. So that's going to be this near.ai/Shade route.